Morning, Bill here. Short little video today on linear algebra. I mentioned this in class the other day and got a couple of funny looks there. Not even a whole class on linear algebra here. We just want to very quickly talk about vectors. And let me see what's going on here. There we go. Give me a moment, please. Let's get a bigger line. There we go. So we're talking about vectors. And I know that this is going to be review for all of you, something you haven't seen in a while. So we're just here to sort of reinforce something from long ago. So we'll start off very easy here. And I've got the y-axis and I've got the x-axis here. And I want to distinguish between two different things here. I want to distinguish between a point which might have an x-coordinate and a y-coordinate, like 3 and 4. And that would mean we'd come over here to 1, 2, 3. And we go up here to 1, 2, 3, 4. So we'd come over here and we'd call that point P. And then there's this notion over here of the vector P. And we always denote vectors by drawing a line over it, an arrow. And I'm going to say, let that equal 3, 4. And that's something slightly different. A vector, there are two components to a vector. There's a direction, and then there's also a magnitude. Magnitude is just a very fancy way of saying length. So if I want to talk about this vector P, what that is that means I come over here from the origin and I actually go right over to there and I put an arrow on it like that. So we'll notice, first of all, there's a direction. The direction is off towards this direction right here. And then there's a magnitude, and the magnitude of this thing, of course, would be the length of this vector. So first of all, if we're given a vector like this, if I'm given that vector P is equal to 3, 4, we sometimes use the notation this, double line P. This is asking what is the length of P. And again, you'll notice if we have this vector here like that, we can invoke our old friend Pythagoras, known to all of you. So we will note over here that the length here is 3, the length over here is 4, and using Mr. Pythagoras' theorem, we would say that the length of this thing here would be 3 squared plus 4 squared, and we take the square root of that, and of course that turns out to be 5. Okay, so this would equal down here, it would be the square root of 3 squared plus 4 squared. So in general, if I'm given some vector P, which is equal to some arbitrary AB, then we would say that the magnitude of P is equal to the square root of A squared plus B squared. And again, I hope that so far this is all review for you. A couple of more things we want to say about vectors. If I were to come over here and say go 1, 2, 3, and then come up here 4. As far as we're concerned, that's exactly the same vector. It's got the same direction, okay? We can see that the angle here that it makes with the x-axis is exactly the same. It's also got the same length. So in fact, when we are given a vector like this with a direction and a magnitude, we're actually free to move it wherever we want. Okay, these are all the same vectors right over here. like that. Okay, that comes in handy when you want to do something like add vectors, because it turns out if I have a vector over here, and let's call that vector A, and suppose I come over here and I have this vector B. Now it turns out that if the vector A is equal to A1, let's call that A1, A2, and the vector B is equal to B1, comma B2, then it turns out that the vector A plus the vector B, I can just go ahead and I can add these components. It would be A1 plus B1, A2 plus B2. But pictorially what it means is I could take this vector right over here, and if I wanted to, I could put it right over here. And again, I would want to draw something, and I'm not a good artist. I'd want to draw something that is in the same direction as this one and of the same length. And now this is A and this is B. This point right over here would get me the head of the vector A plus B. And again, I hope this is all review to you. We know that if I have a vector that looks like this, that if I multiply it times -1, it has the effect of just turning it around and having it face the other way. Again, I hope that this is all review for you. Okay? Next thing, I want you to imagine that I've got my coordinate axes here, X and Y. And I want you to imagine that I draw a vector here, and I want you to suppose that the length of this vector is 1. And I want you to imagine that I have this angle here, theta. And I want you to think about this triangle that happens here when I project this down onto the x-axis. Now we have to go back and talk about some trigonometry. So if I were to ask you about what is the cosine of theta, and if I were to ask you about what is the sine of theta and the tangent of theta, you have to remember some goofy thing that you learned back in high school. And I think, what was the goofy thing that I learned? I think we learned SOHCAHTOA. Sounds like a vegetable dish. But that basically says that sine is the opposite over the hypotenuse. And the cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent, which you may remember is also equal to sine of theta over the cosine of theta. So what this means over here, if we come over here, so I'm basically, I don't think we're ever even going to talk about sine. We're just interested in the cosine of theta. And I want you to notice that if we're looking at the cosine of theta, I've got a 1 here, okay? So here is the opposite. Here is the adjacent here. And notice in this situation here, I've got a hypotenuse of 1. So this is just equal to the adjacent. The cosine of theta is just this length right here, between here and here, okay? And in fact, I think you can also see by looking at the sine of theta is just going to be, if I came over here and I projected this onto the y-axis. So the distance from here to here is the sine of theta. So the cosine of theta is always the projection onto the x-axis, and the sine of theta is always the projection onto the y-axis. So there are a couple of things I want you to note here. I'm going to draw two of these for reasons that will become apparent to you very quickly. If theta is 0, then this thing is pointing out here like this. Okay? And theta is 0, so that the cosine is just the length of this thing right over here, which we said is 1. So the cosine of 0 is 1. So I'm going to come over here, and I just want you to note that the cosine of 0 is equal to 1. Now likewise, if I came over here and I was pointing this thing, if I had this thing pointing straight up, again, just imagine moving this thing around to here, the projection onto the x-axis would be 0. Now theta in that case, I'm going from here to here, is 90 degrees, or pi over 2, so I have that the cosine of pi over 2 is equal to 0. So if I came over here to pi over 2, cosine kind of goes like that. If I came over here and now I'm at pi, or 180 degrees, we can see the cosine is -1. It comes down to here. So that's like right over here. Like that. And it comes back over here. And if I were to continue this argument, this would be 3 pi over 2. And then it comes back up here. And that over here would be 2 pi. So this is the graph right here of y is equal to cosine theta. Now, I hope I'm not worrying people too much. And believe it or not, for this class, the only thing we have to worry about is right in here, between 0 and pi over 2. Basically, what you need to remember is that fact right over there. And we'll see a little more of that in a moment. Okay, finally, I want you to recall, hang on here, just getting my technology up with me, this thing called the dot product. That's if you're American. If you're from anywhere else in the world, I think they refer to it as the scalar product. And there are a couple of things here. It said that if you have a vector A and you had a vector B, you can talk about this thing called the dot product, A dot B. And we actually, you may recall there were a couple of definitions of it. One definition would be this is equal to A1 B1 plus A2 B2. And again, if you're into cool notation, using sigma notations like that, that's I equals 1 to 2 A sub I B sub I. That's one way we defined it. And there was another way that it got defined there, which that this was equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. That's assuming that A goes that way, and maybe B goes that way, and here's theta, which is the angle between them. I'm not going to prove that this equals that, but why don't we consider an example? Why don't we come over here and suppose why don't we have A is equal to 1, 1. And let's come over here and let's have b equal to 2, 0. Now, according to our first calculation here, a dot b is equal to a1, b1, so that'd be 1 times 2 plus 1 times 0 is equal to 2. Okay? In the second situation, let's calculate the magnitude of A. Okay, so the length of A is equal to radical 2. Again, and if I come over here and I calculate the length of B, well, that's easy. That is just going to be 2 squared plus 0 squared. And I take the square root of that, and that's equal to 2. And I think you all realize that if this is 1, 1, and this is along the x-axis, then theta here, that's 45 degrees, and 45 degrees is what? That's pi over 4. And now I need to know what is the cosine of pi over 4. And I think you're all getting very nervous, which you shouldn't be. Because if I come over here, pi over 4, that's a 1, 1, 2 triangle, if you will. If that's 1, and that's 1, and that's radical 2, and this over here is pi over 4. Okay, then the cosine of pi over 4, remember that is equal to the adjacent over the hypotenuse. Well, the adjacent is 1, and the hypotenuse is radical 2. So now I have that the magnitude of A times the magnitude of B times the cosine of theta is equal to, let's see, that is radical 2 times 2 times the cosine of theta, which is 1 over radical 2. Those cancel out, and this is equal to 2, which is exactly what we got when we calculated the dot product the other way. So I just showed you this to convince you that you do get the same answer here. Now, here's what's going to be important to us right here. Listen closely, and this is very easy. We come over here and we consider A dot B, and we say that that is equal to the magnitude of A times the magnitude of B times the cosine of theta. Well, that says to me that A dot B over the magnitude of A times the magnitude of B that's equal to the cosine of theta. Okay? Or to put it another way, don't be frightened, this is easy, that theta is equal to the inverse cosine of A dot B over the magnitude of A times the magnitude of B. Everybody okay so far? So we're almost at the punchline here, okay? First of all, note that the cosine of theta, okay, always goes between -1 and 1. So that this number over here is always going to be a number between -1 and 1, okay? But we know, I'm going to tell you something else. when we go ahead and calculate these numbers, it's going to turn out that the numbers the A's and the B's are all going to be non-negative numbers. In other words, we're going to have A's that might look like this. 3/4, 1, 2/3. Now I know I'm getting into higher dimensions here, but so there's a 4-dimensional A, and here's a B over there, and this might be 0, 0.3, 2.75. We're only going to be we're only going to be dealing with vectors that have components that are non-negative, okay? So in fact, what is going to happen over here is that this quantity right here that I've drawn is always going to be greater than or equal to 0, and it's always going to be less than or equal to 1. Well, I want you to go back and think about what that means here. First of all, we noted back here when we talked about cosine, okay, that the cosine of 0 is 1, and the cosine of pi over 2 is 0. So what that tells me over here, in this calculation over here, if I'm dealing with A's and B's that are always going to have non-negative components in here, that what's going on is that the angle between them is always going to be between 0 and 90 degrees. In other words, if I come over here and here's A, and I come over here and here's B, and these are vectors, this angle over here is always going to be between 0 and 90 degrees. That's a very, very important fact to keep in mind here. And in fact, what we're going to be doing here, we've spoken about this a little bit in class already, we are going to be talking about the similarity between documents, between URLs. And what we're going to be doing is we're going to be expressing those URLs as vectors. And what's going to happen, believe it or not, the URLs are going to, I can't find my cursor, there it is. They're going to look like this. They're going to look like vectors. And they're going to be vectors of non-negative numbers. And what we're asking for is we're asking for how similar are these two vectors. We're going to go ahead and we're going to calculate this quantity over here. Okay? If what we get back here is a number that's closer to 0, meaning that the vectors may look like this. Here's A, and here's B. We're going to say that these vectors are much more similar than a situation where I've got A over here and B is up there like that. So remember, if you take a look at theta over here, theta here is closer to 0. Theta here is closer to pi over 2. When I calculate this quantity here, for this A and B, I'm going to get a number that's closer to 1. When I calculate this quantity here, I'm pointing over here in case you can't see it, for this quantity here, it's going to be closer to 0. Okay? We will see this more in class. That is the end of the video. I hope you all enjoyed it, and I just need to find the stop button.